We will now define noise power at the output in terms of noise factor F. So what I've done is I've taken an amplifier. Let's say this is an amplifier to which we are applying an input signal with input noise power PSI and input noise power PNI. On the output side, the output signal will have signal power PSO and the noise power PNO. The question is the right now what we are going to discuss is what will be the expression of output noise power in the form of the noise factor. The noise factor, please remember, is related to all these four values. Now let us start with the expression of the noise factor. The noise factor we have just now defined will be PSI upon PNI into PNO upon PSO. This is the expression of the noise factor. Now we define something called as power gain of the amplifier. Power gain of the amplifier is written with letter capital G, and it is nothing but the ratio of the output power to the input power. When we consider this ratio, we only consider the signal power and not the noise power. So G is, remember, the power gain. This is similar to the voltage gain, which is output voltage upon input voltage, or current gain, which is output current upon input current. This is power gain in this case. So if I use the notation of power gain, then the noise factor becomes, you can see, I can replace this PSI upon PSO part. So noise factor will become PNO remains, PNO remains, PNI also remains. Now G is PSO upon PSI. We here have PSI upon PSO. So PSI upon PSO will be 1 by G, so that G comes in the denominator. So we have expressed noise factor in the form of power gain and input output noise. From this we get the expression of output noise power, which will become F G PNI. Now further, if I already know that the input power is due to the, let's say due to the presence of a noise source in the form of a resistor or conductor at the input of the amplifier, then we have already defined the power due to such a noise source, which could be a thermal noise source. In that case, the power is simply given as PNI equal to KTB. We have defined the thermal noise power as KTB. So if let's say the source of input noise is nothing but the thermal noise, then PNI will be KTB, and therefore the output noise PNO will become FG, and PNI will be nothing but KTB, where K, TB are as per their usual notations, and G is the power gain of the amplifier, and F is the noise factor. Ideally, we had seen that noise factor should be equal to 1, and therefore PNO should be equal to GKTB, which makes a lot of sense because G is nothing but PSO upon PSI, and KTB is nothing but input noise power PNI. So PNO has to be equal to PSO upon PSI into PNI, something that we have already considered before. If F is equal to 1, then PNO will be nothing but all these terms will go on the other side, and this is what we get. But this is only the case ideally. In practice, F will always be a value greater than 1, and hence noise power will very much depend, the output noise power will very much depend upon how much the amplifier is adding noise to the input signal. The next parameter, which is frequently used in the representation or the measurement of noise, is called noise figure. Now noise figure is closely related to SNR. We have defined SNR as nothing but the signal to noise ratio, PS by PN. We went on to define noise factor in case of an amplifier or any system which adds noise to the input signal. F was nothing but signal to noise ratio on input side divided by signal to noise ratio on output side, which later on turns out to be PSI upon PNI into PNI upon, sorry, PNO upon PSO, and this value is always greater than 1 practically. Now what is noise figure? Noise figure is nothing but, as we can write it as NF, is nothing but noise factor measured in dB. So it is nothing but noise factor represented in dB. So therefore noise figure is equal to, now how can I convert the value of noise factor in dB? It will be nothing but 10 log of f. So 10 log of f to the base 10 will give me the noise figure. Now if I represent this in the form of power values, we know that f is nothing but the noise factor is nothing but SNR on the input side upon SNR on the output side. If I separate this out, we get 10 log SNR on the input side to the base 10 minus, because the two values are being divided and then we are taking log, I can separate them using minus. This is 10 log of SNR on the output side to the base 10, and this becomes this is nothing but SNR on the input side in dB minus this is nothing but SNR of the output side in dB. So the difference between SNR values in dB on the input and output side is nothing but the noise figure. So whenever we are dealing with SNR in dB and not in terms of normal value, in that case it makes more sense to use noise figure instead of noise factor, because noise figure can be simply obtained by subtracting the SNR values which are represented in dB. So because we have just now seen that SNR on the input side will be greater than SNR on the output side, like noise factor, noise figure will always be greater than 1. Ideally, because we say that noise factor should be equal to 1, noise figure, which is nothing but 10 log of noise factor, 10 log of 1 will be nothing but 0. So ideally noise figure should be 0, which indicates that the amplifier or the system under consideration is not going to add any noise to the